So what if we deform something beyond just a little bit? What if we go beyond what Hooke's law is talking about? Hooke's law is saying, oh, if you stress it a little bit, then it obeys this proportionality constant. But what if we stress it more so that Hooke's law isn't applicable anymore? So if you stress anything hard enough, it'll break, right? Is there something more that we can say here other than, oh, if you stress it more, then it breaks? Well, sure, because each material is different. Each material has a different breaking point, and each material acts a little bit differently, even within, even just past Hooke's law, before it breaks. And there's entire fields of study that are devoted to this as well. Field of materials science and mechanical engineering and construction management, and even in the corporate world, the product testing, stress testing of products is a huge component of any company that sells a physical product. So here's a typical stress-strain diagram. We're going to make a sacrifice today, or you are going to make a sacrifice. Take a mechanical pencil or pen, whatever you're writing with, or if you're writing with not a mechanical one, find something that acts like the little tab here. So take your pencil, and we're going to play with that little tab there. All right, so let me get this nicely in view for you, see if that works. Yeah, that looks okay. Okay, so Hooke's law is this range here, right? So what are we looking at? This is stress on the vertical axis and strain on the horizontal. So stress goes up, strain, and this here, this linear part here, that's Hooke's law. That's that proportionality factor, right? It's completely elastic. It's ideally elastic. This is the limit of Hooke's law. It's the proportional limit. It stops being proportional. And this is for a malleable metal, but it also works similarly for your plastic, the plastic tab there. Beyond here, we get into the realm of plastic deformation. And what that means is it's not going to, once you stop bending it, it's not going to go back to where it came from. So do this. So we're going to start here, and we're going to make our way along this curve, okay? So take the tab of your pencil and pull it just a little bit. Not so that it permanently deforms it at all, just a little bit so that it snaps right back. So that it acts like a spring. That is in this region here, right? Then, when we get to here, this is the point where if you bend it beyond that point, it does not come all the way back to where it was. If you bend it beyond that point, so like let's say C, and then you release it, so that's hard to see. You have bent it. That's your pencil, and this is the tab. You've bent it quite a bit, and so then it comes back. It's not going to come back to where it was. It's going to still be sticking out a little bit, if that makes sense. So that is this line here. If you bend it to this point, you let go, it wasn't completely elastic. It doesn't go all the way back to there. It comes back to here. It's a permanent set. And if you go beyond that, at some point, so keep bending it slowly, until at some point, maybe it snaps or it completely bends. So this is the fracture point, the point at which if it's a metal tab, it might actually snap. If it's a plastic tab, it might just deform so much that it turns white. But this is that point where it's completely broken, the fracture point. All right. Hopefully you thought that was a worthy sacrifice of a pencil tip, or a pencil tab thing. Okay, and then just for one more, here's a very stretchy thing. This is vulcanized rubber. Stress strain diagram for vulcanized rubber. That's the stuff of car tires and bike tires and stuff. So this is as you're stretching it. And then this is the stress strain curve for decreasing stress. So it's springing back. So if this stuff interests you, this is about where we end here, and we're going to move on to something completely different next topic. we're going to move on to fluid dynamics, or fluid mechanics. But if this stuff interests you, you might consider looking more into the field of material science. If you really want to see odd material behavior, if you're not quite convinced that this stuff is interesting, then do this right now. Search in YouTube nitinol. I'm going to write that out. There's a material called nitinol. And it's so called that because it is a composite of nickel and tin. And it was discovered at nickel and titanium. That's what it is. Nickel, titanium, and then it was first observed at the Naval Ordnance Laboratory. So that's where the name comes from. But YouTube nitinol, and that material has some interesting properties. It's called a shape memory alloy, and it can hold memory of a certain position that it was in. Even if you completely deform it and you drop it in warm water, it comes all the way back to that remembered shape. It's the stuff of magic. But there is an explanation for it, of course. All right, that's it for this lecture.